So I would also like to thank Elspeth. A few of the things you mentioned are going to be said again. I think we agree on most things. I'm reporting about a project that is not mine. It's predictive failure. Many of you know Manu Kapoor brought productive failure to the ETH. We are in collaboration with him, and I'm reporting about that project. Before we do that, however, I asked myself in preparing this presentation the question whether failure in mathematics is different from failure in natural sciences or engineering. And I think in some sense that it is, and some sense that it is not. And I think we need to distinguish two cases. Mathematics consists of computations. That's what a lot of the ETH students do in their engineering and natural science degrees and what they need. And there are proofs. And that's, of course, especially what mathematicians do. And here I think there is a difference that in mathematics literature, people report about proofs that they have proven, and they sometimes report about things that cannot be proved. That's also very important. But you hardly ever or never see papers about what they didn't manage to prove. And I think that's different in the other subjects, especially if there are experimental questions with labs. And so I think it's very important to communicate what did not work. And maybe it should also be communicated more in mathematics, so that not everybody tries to prove the same thing the same way if that doesn't work. But I think there are some differences that may be interesting. But for our engineers, and I'm talking about the engineering education of the ETH, this may not be the focus. Now, this picture, you know, he was the one who suggested that I talk. He should have talked, but he couldn't make it. This is Manu Kapoor, professor at the ETH, and predictive failure is his baby, I think. For those of you who do not know what this is, I mean, this is a slogan. If learning from failure is intuitively so compelling, why wait for it to happen? Why can't we deliberately design for it? And I think that's a very good point. I mean, we all know, Elspeth already said it, Philip also said it in the beginning, learning happens through mistakes. That's the way to learn, that's the way to keep things. Why can't we produce this artificially? And Manu has a very beautiful example with the standard deviation, which is done with many students all over the world. And it works at all levels. It doesn't only work for clever students. It doesn't only work for weaker students. It works for all. It's a very nice example. And we decided in collaboration with him to try this out in a maths lecture. And then we found out that it's not so easy to design these questions. So what is the project? It's a project in a linear algebra course at the MAFT department, Mechanical Engineers. And the team is rather big. The team consists on the one hand of Vera Baumgartner and Simona Daguati, both PhD students, Vera from Manu, Simona from Elspeth, and then Manu Kapoor and his postdoc Dragan Trinic. And from the math side, myself, Alexander Kasper, and Professor Norbert Hunkerbühler. Now, Vera is actually writing her PhD on this topic, and she is trying, if I describe that very briefly, to see if there's a connection between the results that we get from the self-assessment test. We do have a big self-assessment test in the maths department that the students fill out with the work they do in our project and then the results in the exam. First, studies seem to suggest that there is a correlation, and that's what she's trying to work on. Now, what is this project? As said, we do this project with the first year mechanical engineers. That means we have around 600 students. It's one of the very big lecture courses. And this course is taught traditionally and over many, many years by Professor Hunkerbühler. That also guarantees that the course is always taught in more or less the same way, which makes it, of course, easier to compare. Now, what is the project? The project consists, and this is the description for one semester, we do it 2 semesters, so you have to multiply everything by 2, consists of 5 preparatory exercise series per semester. And the preparatory tasks have as a goal to address common misconceptions, and they are solved prior to instruction. Then there is a post-test at the end of the semester to see how well the students have now understood these conceptions. And I think that is the philosophy of the productive failure. Elsbeth already mentioned, I think, both concepts here, common misconceptions. Students do have wrong ideas of how things work or why they don't work. And students have prior knowledge, but it may not always be activated. And these preparatory tasks are designed so that they actually activate this knowledge again. Why do the students take part in this? Of course, we tell them that if they do this, they will learn better, they will get a better grade, it's better for them, but that's all not always convincing. So we have also set up a bonus system. So these preparatory tasks are part of a bonus that the students will get and which will be added to their exam grade. And each task itself gives 1 or 0 points. Also, the participation in the post-test gives 1 or 0 points. And it's really important here, it's just the participation. It doesn't matter how good they are. Of course, they get the feedback, but their result doesn't count. And then this is our usual formula in the maths department, how we then add that to the grade. The preparatory tasks have a very important guide for correction, and they're corrected by our teaching assistants. So we do extra instruction for the teaching assistants to correct these tasks, because we want to, it's not even correcting, I think. We want, the main focus is effort over correctness. So they get their point if they try every exercise, even if they do it completely wrong. That does not matter, as long as we see that they made an effort. So the answer should be in some sense related to the tasks, but then they get the answer. If they very briefly only give numerical correct answers, but do not explain them when that is asked, they get no points. So it's a different strategy, which is not very common at the ETH. In the exams, we usually count correctness, but that's very important here. It's not about correctness. It's about being involved. Now, when we started this project, we talked to Manu, and the philosophy was predictive failure. And then we realized it's not easy to create those tasks. So we try to build in more aspects, and sometimes even only those are in there. But the guidelines are, first of all, predictive failure, then to activate prior knowledge, to increase motivation, sometimes useful applications, and sometimes using contrasting cases to, for example, increase motivation. And all this happens before the lecture. So the students have to, or get these bonus exercises before the relevant lecture, and have to hand in the bonus exercises before the lecture. And then during the lecture, Professor Hunkerbühler explains why this question was set, maybe what the answers are, and what the theory is that actually makes you understand this. Now, I've tried to think of one of the examples that we gave. They are long exercises, as you will see in a minute. I've tried to find an example that is understandable to non-mathematicians. And I tried to find an example that fits in well with the predictive failure concept of Manu Kapoor. And the one that I chose is the determinant. I think many of you know the determinant. It's an important concept in linear algebra. And it relates to various topics. Here in particular, the vector product, the area of a parallelogram, and the existence of a solution of a linear system of equations. So 3, at first sight, maybe not related concepts, which they all know. Now, I didn't translate the exercise. It's also not so important. The first question is about the vector product. They've learned that in school, and the first questions are to compute it, and there are special vectors, and we have special coordinates, and they have to think about the meaning of that vector product. I'm not going to go slowly through this. You're not supposed to solve it, but it's just to get an idea of what it's about. Then a little more, some others, also about the commutativity or not of the vector product. It's all in there. And then the second question changes the picture. It's two-dimensional. We have a parallelogram. We call the vectors the same, and we compute the area with elementary geometry. And then the third one, something they are used to by this time, to solve the linear system of equations 2 by 2, again, these same letters. And then question 4 is actually the important one. Compare your results. What do you observe? Now, this is where something should happen. And that's how I would like to sort of finalize here. First of all, we activate prior knowledge. They need vector geometry, they need systems of linear equations. They have to go through all of it here. And then they see the same expression, this A1 times B2 minus A2 times B1, over and over again. And they probably don't know why, which results in some sort of failure. We ask them what happens and they can't explain. Now, hopefully, and I think this really happens, this arouses their curiosity. And that means it increases their motivation. They want to know what's happening. And that's when they come to the lecture, and when productive failure has happened, because they're motivated, they come, they want to hear why this is so. So I think it's a beautiful example that illustrates this philosophy. And it also shows that, yes, they fail, they make the mistake here is in not understanding what the connection is, but it opens up for further learning. Now, what's maybe briefly going through this, predictive failure is obviously there. We have activated prior knowledge, motivation has increased. These two, maybe not, but they're not always necessary, they're not always in every case there. But I think it sort of illustrates how we try to use predictive failure to increase the learning in the lecture and increase the understanding of the students. Thank you for your attention.